In this present lecture, we are going to learn partial derivatives, the gradient of a scalar field, the properties of the gradient of a scalar field. At last, we solve a few problems in our present lecture. This topic poses a few questions to us. In this topic, we encounter these questions. How to find out a normal to a given surface. Next, we have to answer a question how to find out a unit normal to a given surface at a given point. Next, we have to solve a question how to find out angle between two surfaces. Lastly, we have to find the directional derivatives. But I skipped this last question of finding directional derivatives. I explain the process of finding directional derivatives in my next lecture. In this present lecture, we try to solve all the remaining questions. Let us recall partial derivatives. Here, first we consider a function f from R2 to R. This function is a function of two variables. This function is also called a scalar field or a scalar point function. Because this function is a function of two variables, there are two partial derivatives. The first one is dou f by dou x, and it is defined by the formula limit h tends to 0 f of x plus h comma y minus f of x comma y upon h. The second partial derivative is defined by dou f by dou y equals limit k tends to 0 f of x comma y plus k minus f of x comma y upon k. We know very well that while finding dou f by dou x, we allow x to vary and we treat y as a constant. Similarly, while finding the next partial derivative dou f by dou y, we treat x as a constant and allow y to vary. These two partial derivatives are derivatives in the direction of x-axis and in the direction of y-axis respectively. Here we consider the next case. We consider function from R3 to R. This is also a scalar field defined on the three-dimensional space. So there exist three types of partial derivatives: dou f by dou x, dou f by dou y, and dou f by dou z. The first partial derivative dou f by dou x is defined by limit h tends to 0 f of x plus h comma y comma z minus f of x comma y comma z upon h. The next partial derivative dou f by dou y is defined by the formula limit k tends to 0 f of x comma y plus k comma z minus f of x comma y comma z upon k. The last partial derivative is given by dou f by dou z equals limit delta tends to 0 f of x comma y comma z plus delta minus f of x comma y comma z upon delta. Why we consider these partial derivatives for functions of several variables? We see that functions of single variable, they have differentiation concept. But in the case of functions of several variable, we can't define the derivative as in the case of functions of a single variable. So here we have the concept of partial derivatives. Actually, dou f by dou x is a slope of the given surface in the x direction. Similarly, dou f by dou y and dou f by dou z represent the slope of the surface in the y direction and z direction respectively. Let us see an example here. I have taken a function f of x comma y equals tan inverse of x by y. For this function, let us find out these partial derivatives. Dou f by dou x, dou f by dou y, dou square f by dou x square, dou square f by dou y square, and dou square f by dou x dou y. First, if we evaluate dou f by dou x by treating y as a constant, and if we allow x to vary, then we get the answer y by x square plus y square. If I take dou f by dou y, we get minus x by x square plus y square for this particular function f of x comma y equals tan inverse of x by y. If we find out the second partial derivative dou square f by dou x square, that means dou by dou x of dou f by dou x, we get minus 2xy by x square plus y square whole square. If I find the next second partial derivative dou square f by dou y square, we get 2xy by x square plus y square whole square for this particular scalar field f of x comma y equals tan inverse of x by y in two variables. Lastly, if I find dou square f by dou x dou y, or if I find dou square f by dou y dou x, we get the same answer x square minus y square upon x square plus y square whole square. For this function, these two partial derivatives are equal. Here, dou f by dou x, dou f by dou y are called first partial derivatives of the given function. Dou square f by dou x square, dou square f by dou y square, dou square f by dou x dou y, and dou square f by dou y dou x are called second order partial derivatives. In this particular example, the last two partial derivatives dou square f by dou x dou y and dou square f by dou y dou x are equal. But for some functions, these two partial derivatives may not be equal. So, for some functions, we have to remember that dou square f by dou x dou y is not equal to dou square f by dou y dou x. The main focus of this lecture is the gradient of a scalar field. So, here first we consider a function f from R2 to the real line R. This is a scalar field defined on the two-dimensional space R square. Now, we have already seen that such a function has two partial derivatives, dou f by dou x and dou f by dou y. We use those two partial derivatives to define the gradient of this particular scalar field. The gradient of this function is defined by grad f or del f equals I cap dou f by dou x plus j cap dou f by dou y. Here I cap is a unit vector ordered pair 1, 0 and j cap is the unit vector in the y direction 0, 1. Here del f or grad f is the symbol used to denote the gradient of this function f of x comma y. Actually, z is equal to f of x comma y represents a surface. For this surface, we find the gradient. Del symbol is also called nabla. So, we can read it as gradient of f or del f or nabla f. Now, let us consider the next case, a function from R3 to the real line R. This function is a scalar point function defined on the three-dimensional Euclidean space R3. We know this function has three partial derivatives, dou f by dou x, dou f by dou y and dou f by dou z. So its gradient is defined by gradient of f or grad f or del f equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z. Here we can observe one fact. Here the function is a scalar point function, but the gradient is a vector point function. We must remember one point. The gradient of a scalar point function is always a vector field. So, if I want to call del f a vector field, I have to assign a magnitude and a direction to del f. Then only I can call it a vector. So, what is its direction? What is the magnitude of del f? Let us see. Actually, if we take a function f from R3 to R, now del f is always perpendicular to the given surface f of x comma y comma z equals a constant. This equation f of x comma y comma z equals c represents a level surface and del f is always perpendicular to this level surface. In other words, we can say del f is a normal to the surface f of x comma y comma z equals c. Now, what is the magnitude of this del f? The magnitude of del f can be interpreted in two ways. But let us restrict ourselves to this formula only. The magnitude of del f is given by the formula norm del f equals square root upon dou f by dou x whole square plus dou f by dou y whole square plus dou f by dou z whole square. So, I assigned a magnitude and a direction to the gradient. So, one point is clear. The gradient of a scalar point function is always a vector field. Let's see a few examples. As a first example, let's consider a scalar point function on R cube given by the formula f of x comma y comma z equals xy plus yz plus zx. If we want to find out the gradient of this function, we have to first find out dou f by dou x, dou f by dou y and dou f by dou z. Dou f by dou x for this function equals y plus z. Dou f by dou y equals x plus z and dou f by dou z equals x plus y. Now, the gradient of this function is gradient of f or del f equals I cap y plus z plus j cap x plus z plus k cap x plus y. So, this gives the gradient of the given scalar point function. Our second example is g of x comma y comma z equals xyz plus y square. For this function g of x comma y comma z equals xyz plus y square, if we find out the partial derivatives dou g by dou x, dou g by dou y and dou g by dou z, we get dou g by dou x equals yz, dou g by dou y equals xz plus 2y, dou g by dou z equals xy. Now, what is the gradient of this particular scalar field g? It is del g. Del g equals I cap dou g by dou x plus j cap dou g by dou y plus k cap dou g by dou z. Now, we have to just plug in our values of partial derivatives here. Then we get del g equals I cap yz plus j cap xz plus 2y plus k cap xy. As a third example, let us take a scalar point function defined on R3 as u of x comma y comma z equals x sin y minus z cube. For this function, dou u by dou x equals sin y, dou u by dou y equals x cos y, dou u by dou z equals minus 3z square. If we want to find out del u, the gradient of this u, we get grad u equals I cap dou u by dou x plus j cap dou u by dou y plus k cap dou u by dou z. Now substitute the partial derivatives of u here in this formula. Then we get gradient of u equals I cap sin y plus j cap x cos y plus k cap times minus 3z square. Now we require total derivative formula to use it in our further work. Here, let us consider a scalar point function f defined on R3. So here, f is a function from R3 to the real line R. Now, let us take this formula df equals dou f by dou x dx plus dou f by dou y dy plus dou f by dou z dz. This is called total derivative of f. Now, let us derive a small formula here. First, let us consider a vector r cap equals I cap x plus j cap y plus k cap z. This vector is called a position vector. Sometimes it is also called velocity vector. Now, if I find out dr cap, we get I cap dx plus j cap dy plus k cap dz. This denotes the tangent at that point xyz. So, dr cap is a tangent vector at that point xyz. Now, let us take the dot product between the gradient of f and this dr cap. If del f is dotted with dr cap, Let's see what happens. Del f dot dr cap equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z dotted with I cap dx plus j cap dy plus k cap dz. If we perform this dot product, we get dou f by dou x dx plus dou f by dou y dy plus dou f by dou z dz, which is nothing but df. So, if we take the dot product between these two vectors del f and dr cap, then the result is df. So, df equals del f dot dr cap, which is a very important formula which is to be used in the further work. Let's understand the direction of the vector del f in detail. Here, let's consider a scalar point function f defined on R3, the three-dimensional space. Let us suppose that w equals f of x comma y comma z. Consider a level surface f of x comma y comma z equals c. Here c is a constant. Now, because f is a constant, its total derivative df is 0. Because f of x comma y comma z equals c, df becomes 0. What is df? We derived one formula for df. Del f dot dr cap equals df. Because df is 0, del f dot dr cap becomes 0. If the dot product between two vectors is 0, what we can say about them? Those two vectors are orthogonal to each other. Here, del f and dr cap are orthogonal to each other because their dot product is 0. Dr cap represents the tangent vector, so del f represents a normal vector. So del f is always perpendicular to the given surface. The gradient of a scalar field satisfies a few properties. This gradient of a scalar field behaves like a derivative of a function of single variable. If we take two scalar point functions f and g, we can observe the following properties of the gradient. The first property is del of f plus g equals del f plus del g. The second property is del of cf equals c times del f, where c is a constant. The third property is del of fg equals f del g plus g del f. The last property is del of f by g equals g del f minus f del g upon g square. These properties are very easy to prove. These properties depend on the properties of the partial derivatives dou by dou x, dou by dou y and dou by dou g. So, for example, if we want to prove del of f plus g, what is del of f plus g? I cap dou by dou x of f plus g plus j cap dou by dou y of f plus g plus k cap dou by dou z of f plus g. It can be written as I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z plus I cap dou g by dou x plus j cap dou g by dou y plus k cap dou g by dou z. It in turn becomes del f plus del g. So we can prove del of f plus g equals del f plus del g. Similarly, we can prove the remaining properties. Here, from the first and second properties, we can say the gradient is a linear function. That means the gradient satisfies the linearity property. The gradient of a scalar field has many applications. We have to solve a few problems to understand these applications of the gradient. As a first problem, let us take a scalar field defined on the three-dimensional Euclidean space R3. Let u of x comma y comma z equals 5x square yz. In this problem, they asked us to find out the gradient of the scalar field u and its magnitude norm of del u at the prescribed point. So let us find out them one by one. Consider the given scalar field u of x comma y comma z equals 5x square yz. If we want to find out its gradient del u, what we have to find first? We need to find out its partial derivatives dou u by dou x, dou u by dou y and dou u by dou z first. Dou u by dou x of this u of x comma y comma z equals 5x square yz is 10xyz. Dou u by dou y equals 5x square z and dou u by dou z equals 5x square y. What is del u? The gradient of u or del u equals I cap dou u by dou x plus j cap dou u by dou y plus k cap dou u by dou z. Now plug in the values of the partial derivatives here in this formula. Then del u equals I cap 10xyz plus j cap 5x square z plus k cap 5x square y. This is the gradient of the given scalar field u. But we have to find out del u at the given point 1, 0, 1. Here the value of x is 1, y equals 0 and z equals 1. If I substitute these values of x, y and z, then del u becomes del u equals j cap into 5. That means del u equals 5j cap at this particular point. The magnitude of this del u is norm del u. So norm del u at this given point 1, 0, 1 becomes square root over 5 square, which equals 5 again. So in this problem, del u at the given point becomes 5j cap and the norm del u is 5. Problem number 2. In this problem, a surface is given phi of x comma y comma z equals x cube plus y cube plus z cube. They asked us to find out a unit normal to this surface at the point 1 comma 2 comma minus 1. We have already studied that unit normal to a given surface is nothing but the gradient of the given surface at the given point. Let us find out unit normal to this given surface. First consider phi of x comma y comma z equals x cube plus y cube plus z cube. For this surface, if I want to find out a normal, what I need to find out? Its gradient. Before finding the gradient, we need to find out its partial derivatives dou phi by dou x, dou phi by dou y and dou phi by dou z. Dou phi by dou x equals 3x square, dou phi by dou y equals 3y square and dou phi by dou z equals 3z square. For this surface, phi of x comma y comma z equals x cube plus y cube plus z cube. The gradient of this surface phi of x comma y comma z equals x cube plus y cube plus z cube is del phi equals I cap dou phi by dou x plus j cap dou phi by dou y plus k cap dou phi by dou z. If we substitute the values of the partial derivatives here, we get del phi equals 3x square I cap plus 3y square j cap plus 3z square k cap. This is the gradient of the given surface phi. But we want this gradient at the given point 1 comma 2 comma minus 1. So here x value is 1, y value is 2 and z value is minus 1. If we substitute x, y and z values, we get del phi equals 3i cap plus 12j cap plus 3k cap. This is the value of the gradient of the given surface at the given point. This is also called a normal to the surface at the given point. But we want unit normal. Unit normal means what? The length of the normal must be 1. Length means norm. So we have to find out norm del phi at the given point. So if del phi equals 3i cap plus 12j cap plus 3k cap, then norm del phi equals square root upon 9 plus 144 plus 9, which equals square root upon 162. If we want to find out the unit normal at the given point, we have to use this formula del phi upon norm del phi at this given point. If I suppose n cap is the unit normal of the given surface, phi of x comma y comma z equals x cube plus y cube plus z cube at the given point 1 comma 2 comma minus 1, then the unit normal n cap equals del phi whole divided by norm del phi at this point, which equals 3i cap plus 12j cap plus 3k cap upon square root over 162. This is the unit normal of the given surface at the given point. Thus, we can find out unit normals of the given surfaces by using the gradient. This is one of the applications of the gradient. Problem number 3. In this problem also, we have to find out a unit normal to the given surface at the given point like the previous problem. In this problem, the given surface is x square y plus 2xz is equal to 4. We need to find out a unit normal to this surface at the point 2 comma minus 2 comma 3. To find out the unit normal, first let us consider the surface f of x comma y comma z equals x square y plus 2xz minus 4. To find out a normal or unit normal, we need to find out its partial derivatives dou f by dou x, dou f by dou y and dou f by dou z. For this given surface, f of x comma y comma z equals x square y plus 2xz. The first partial derivative dou f by dou x equals 2xy plus 2z. Dou f by dou y equals x square. Dou f by dou z equals 2x. Now, we have to find the normal. Normal to the surface means gradient only. It is sufficient if we find the gradient. For this surface, del f equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z. Here we have to plug in our values of partial derivatives. Then gradient of f or del f equals I cap times 2xy plus 2z plus j cap times x square plus k cap times 2x. This is the gradient of the given surface f of x comma y comma z is equal to x square y plus 2xz. We have already found the gradient of the given surface f of x comma y comma z equals x square y plus 2xz minus 4. Now, del f at the given point 2 comma minus 2 comma 3. This we have to find out now. The del f at the given point is minus 2i cap plus 4j cap plus 4k cap. This is the gradient of the given surface at that given point 2 minus 2 3. We want the unit normal. Up to now we found the normal to the given surface at the given point. To find the unit normal, we have to find out the magnitude of the del f. The magnitude of del f means norm del f. First, del f is minus 2i cap plus 4j cap plus 4k cap. So, norm del f equals square root over 4 plus 16 plus 16, which equals square root over 36, that is equal to 6. So, norm del f equals 6. The unit normal to the given surface x square y plus 2xz equals 4 at the given point 2 comma minus 2 comma 3 is given by the formula del f upon norm del f at the given point. So this value of del f divided with norm del f equals 1 by 6 times minus 2i cap plus 4j cap plus 4k cap. If we take 2 outside, it cancels with the denominator 6 and we get the answer 1 by 3 times minus I cap plus 2j cap plus 2k cap. But here we have to observe one fact. Why this value del f by norm del f is called a unique normal? Suppose that n cap equals this del f by norm del f. Then n cap becomes what? 1 by 3 times minus I cap plus 2j cap plus 2k cap. Which is the value of del f by norm del f? It is a unique normal. Why? If you find out its magnitude, that means norm of this n cap, that means norm of del f by norm del f, how much it becomes? It becomes 1. Norm of n cap equals norm of del f by norm del f equals norm del f by norm del f, it becomes 1. Otherwise, even though we find the value norm of n cap equals square root over minus 1 by 3 whole square plus 2 by 3 whole square plus 2 by 3 whole square, which in turn becomes square root over 1 by 9 plus 4 by 9 plus 4 by 9. This again becomes 1. Let us take problem number 4. In this problem, we have to prove a formula. Del r power n equals n r power n minus 2 r cap. Solution. We know that the vector r cap equals I cap x plus j cap y plus k cap z. We have seen this vector already. This vector is called a position vector or a velocity vector. If r cap equals I cap x plus j cap y plus k cap z, then dr cap becomes I cap dx plus j cap dy plus k cap dz. Now, if we want to find out r square, what we have to do? R square equals r cap dot r cap. That means I cap x plus j cap y plus k cap z is dotted with itself. So, r square becomes I cap x plus j cap y plus k cap z dotted with I cap x plus j cap y plus k cap z, which again equals x square plus y square plus z square. So r square equals x square plus y square plus z square. Here we can observe one point. R square is a scalar. Similarly, r power n is also a scalar. It's a scalar point function. Now, take r square equals x square plus y square plus z square. If we differentiate partially with respect to x on both sides, we get 2r divided by x equals 2x. If we cancel 2 on both sides, r divided by x equals x. From this, divided by x equals x by r. Similarly, by taking r square equals x square plus y square plus z square, we can find out 2r divided by y equals 2y, from which we get r divided by y equals y. That gives us divided by y equals y by r. Similarly, divided by z equals z by r. I have already mentioned one point. R power n is a scalar field or a scalar point function. Gradient can be found for scalar point functions only. Because r power n is a scalar point function, we can find out its gradient. Let us find out the gradient of r power n now. Del r power n equals I cap dou by dou x r power n plus j cap dou by dou y r power n plus k cap dou by dou z r power n, which equals I cap n r power n minus 1 dou r by dou x plus j cap n r power n minus 1 dou r by dou y plus k cap n r power n minus 1 dou r by dou z. Here we have to substitute our previous values of dou r by dou x, dou r by dou y and dou r by dou z here. Now what happens? Del r power n equals I cap n r power n minus 1 x by r plus j cap n r power n minus 1 y by r plus k cap n r power n minus 1 z by r. If we cancel r power n minus 1 in the numerator with small r in the denominator, then we get del r power n equals I cap n r power n minus 2 x plus j cap n r power n minus 2 y plus k cap n r power n minus 2 z. From the right hand side, we can take out n r power n minus 2. So what happens? Del r power n becomes n r power n minus 2 times I cap x plus j cap y plus k cap z. What is that vector in the brackets I cap x plus j cap y plus k cap z? That is nothing but our velocity vector r cap. So if we substitute that r cap there, we obtain del r power n equals n r power n minus 2 r cap. So we are done. Problem number 5. In this problem also, we need to prove a formula del f of r equals 1 by r f dash of r cap. To prove this formula, let us consider r cap equals I cap x plus j cap y plus k cap z again. We know that this is our velocity vector. If we want to find out r square, we need to find out r cap dot r cap. So r square becomes x square plus y square plus z square. We have seen this in our previous problem. From this, smaller value is square root upon x square plus y square plus z square. If we observe, r equals root over x square plus y square plus z square, r square is x square plus y square plus z square, f of r. All of these functions are scalar point functions. Now consider r square equals x square plus y square plus z square. From this, let us find out dou r by dou x. Take r square equals x square plus y square plus z square and differentiate this with respect to x partially on both sides. It becomes 2r dou r by dou x equals 2x. From this we get dou r by dou x equals x by r. Similarly, dou r by dou y equals y by r and dou r by dou z equals z by r. We found these values in the previous problem also. Now, to find out the gradient of the given function f of r, let us consider this formula. Del f of r equals I cap dou by dou x f of r plus j cap dou by dou y f of r plus k cap dou by dou z f of r. Del f of r equals I cap f dash of r dou r by dou x plus j cap f dash of r dou r by dou y plus k cap f dash r dou r by dou z. We get this value by differentiating f of r with respect to x, with respect to y, and with respect to z partially respectively. After that, del f of r becomes I cap f dash of r times x by r plus j cap f dash of r times y by r plus k cap f dash of r times z by r. So what we have done here? We substituted the values of dou r by dou x, dou r by dou y, and dou r by dou z, and we got this answer. After that, del f of r becomes I cap f dash of r into 1 by r x plus j cap f dash of r 1 by r y plus k cap f dash of r 1 by r z. So we can take out 1 by r f dash of r outside. So we obtain del f of r equals 1 by r f dash of r times I cap x plus j cap y plus k cap z. This vector inside this bracket I cap x plus j cap y plus k cap z is nothing but our velocity vector r cap. If we substitute that r cap instead of that bracket, we obtain del f of r equals 1 upon r f dash of r cap. We are done. Sixth problem. In this problem, they have given a constant vector a cap. We need to prove the gradient of a cap dot r cap equals a cap again. Solution. What do I mean by a constant vector a cap? Constant vector a cap means, suppose a cap equals a1 I cap plus a2 j cap plus a3 cap. When we say this is a constant vector, if the coefficients a1, a2, a3 are constants, they must not be variables. So a cap equals a1 I cap plus a2 j cap plus a3 k cap is said to be a constant vector if its coefficients a1, a2, a3 are all constants. So let us consider a constant vector a cap equals a1 I cap plus a2 j cap plus a3 k cap, where a1, a2, a3 are constants. Let us consider our velocity vector r cap equals I cap x plus j cap y plus k cap z. These two are vectors. A cap and r cap are vectors. Let us take their dot product. If a cap is dotted with r cap, what do we get? A cap dot r cap equals a1 I cap plus a2 j cap plus a3 k cap dotted with I cap x plus j cap y plus k cap z. So a cap dot r cap equals a1x plus a2y plus a3z. If we observe here, a cap is a vector, r cap is a vector, but their dot product a cap dot r cap equals a1x plus a2y plus a3z is a scalar. It's a scalar point function. So we can apply gradient or del to this scalar field a cap dot r cap. So let us find out its gradient. Del of a cap dot r cap equals I cap dou by dou x of a cap dot r cap plus j cap dou by dou y a cap dot r cap plus k cap dou by dou z a cap dot r cap. That implies the gradient of a cap dot r cap equals I cap dou by dou x of a1x plus a2y plus a3z plus j cap dou by dou y of a1x plus a2y plus a3z plus k cap dou by dou z of a1x plus a2y plus a3z. So, what is the dou by dou x of a1x plus a2y plus a3z? That's nothing but just a1. Similarly, dou by dou y of a cap dot r cap equals dou by dou y of a1x plus a2y plus a3z equals a2. Now, dou by dou z of a1x plus a2y plus a3z is a3. If we substitute these values, then we obtain the gradient of a cap dot r cap equals I cap a1 plus j cap a2 plus k cap a3, which is again a cap. So, the gradient of a cap dot r cap equals a cap. We are done. Problem number 7. In this problem, a surface is given to us. xy is equal to z square. 2 points are given to us. We need to find out normals to this surface at the given points. In our previous problems, one surface is given and only one point is given. There we found normal to the surface at that given point. But here in this problem, only one surface is given, but we need to find out normals at the given two different points. Let us consider the surface f of x comma y comma z equals xy minus z square. Now, to find out a normal to this surface, we need to find out its gradient. Finding normal is same as finding gradient. To find out the gradient of the function f of x comma y comma z equals xy minus z square, we need to find out its partial derivatives, dou f by dou x, dou f by dou y and dou f by dou z. If f of x comma y comma z equals xy minus z square, then dou f by dou x equals y, dou f by dou y equals x and dou f by dou z equals minus 2z. Now the gradient of this particular function is del f equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z. If we substitute the values of the partial derivatives here, we obtain del f equals I cap y plus j cap x plus k cap times minus 2z. But we are given 2 points. Say p equals 4 comma 1 comma 2 and q equals 3 comma 3 comma minus 3. Now we have to find out the gradient of f, which is nothing but normal to the given surface at the point p 4 comma 1 comma 2. To do this, we have to substitute x is equal to 4, y is equal to 1 and z is equal to 2 in del f. So del f becomes I cap into y plus j cap into x plus k cap into minus 2z. If we substitute x equals 4, y equals 1 and z equals 2, we get del f at this point p is del f at p equals I cap plus 4j cap minus 4k cap. Now we need to find out del f at the point q equals 3 comma 3 comma minus 3. At this point x equals 3, y equals 3 and z equals minus 3. If we plug in these values in del f, then del f becomes del f equals 3i cap plus 3j cap plus 6k cap. So far we have found del f at p and del f at q. The del f at p represents normal to the given surface f of x comma y comma z equals xy minus z square at the point p 4 comma 1 comma 2. Del f at the point q represents normal to the surface xy minus z square at the point q 3 comma 3 comma minus 3. But we want unit normals to the given surface at the given points. Let us suppose n1 cap denote a unit normal to the given surface at the point p 4 comma 1 comma 2. Let n2 cap denote the unit normal to the surface f of x comma y comma z equals xy minus z square at the point q 3 comma 3 comma minus 3. Now how to find n1 cap and n2 cap? n1 cap equals del f at p whole divided by norm del f at p. So we have to find out norm del f at p at first. We have seen that del f at p equals I cap plus 4j cap minus 4k cap. So norm del f at p becomes square root over 1 square plus 4 square plus 4 square, which equals root over 33. Similarly, to find out n2 cap, we have to first find norm del f at q. Del f at q equals 3i cap plus 3j cap plus 6k cap. So its magnitude is given by norm del f at q equals root over 3 square plus 3 square plus 6 square, which equals root upon 54. Now n1 cap equals del f at p divided with norm del f at p, which equals I cap plus 4j cap minus 4k cap divided with root over 33. n2 cap equals del f at q divided with norm del f at q, which equals 3i cap plus 3j cap plus 6k cap divided with root over 54. Why we say these two are unit normals? Because these two are unit vectors. That means their magnitude is 1. For example, if we take norm n1 cap, what is norm n1 cap? Norm n1 cap equals norm of I cap plus 4j cap minus 4k cap by root over 33, which equals root 33 divided with root 33, which equals 1. Similarly, norm n2 cap is also 1. So norm n1 cap and norm n2 cap are equal to 1. So they are called unit vectors. Not only that, they are normals to the given surface at the given points. So these two are called unit normals to the given surface at the given points. If we want the angle between these two unit normals, what we have to do? We have to apply angle between two vectors formula. The angle between n1 cap and n2 cap is given by cos theta equals n1 dot n2 whole divided by norm n1 times norm n2. Here theta is the angle between n1 cap and n2 cap. If we find out the value of cos theta equals n1 dot n2 by norm n1 norm n2, we get cos theta equals minus 9 upon root 33 times root 54. Thus, we can find the angle between normals also. This completes the problem. Let us take our next problem, problem 8. In this problem, two surfaces are given and a single point is given. In this problem, we have to find out the angle between these two surfaces at the given point. In our previous problem, only one surface was given, but two different points were given. There, we have found the angle between unit normals to the surface at the given two different points. But here we have to find out the angle between these two surfaces at the given point. In this problem, two spheres are given and a point is given. Finding angle between two surfaces is equal to finding angle between normals to the surfaces at the given point. In this problem, the surfaces are the spheres x square plus y square plus z square equals 29 and x square plus y square plus z square plus 4x minus 6y minus 8z minus 47 is equal to 0. The given point is 4 comma minus 3 comma 2. So let us find out the angle between these two spheres at the given point. Let us suppose that f of x comma y comma z equals x square plus y square plus z square minus 29. It is our first surface. The next surface is g of x comma y comma z equals x square plus y square plus z square plus 4x minus 6y minus 8z minus 47. Let p equals 4 comma minus 3 comma 2, which is our given point. To find out the angle between f and g, first we have to find out the gradients of these two surfaces f and g. Let us first find out the gradient of the first surface f. To find out del f, we need to find out dou f by dou x, dou f by dou y and dou f by dou z. Dou f by dou x equals 2x, dou f by dou y equals 2y and dou f by dou z equals 2z for this function f of x comma y comma z equals x square plus y square plus z square minus 29. Now the gradient of this function f is given by del f equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z. That implies del f equals 2x I cap plus 2y j cap plus 2z k cap. Similarly, we have to find out the gradient of z del G. To find out del G, again we have to find out dou G by dou X, dou G by dou Y and dou G by dou Z. Dou G by dou X equals 2x plus 4. Dou G by dou Y equals 2y minus 6. Dou G by dou Z equals 2z minus 8. Now let us find out del G. Del G equals I cap dou G by dou X plus j cap dou G by dou Y plus k cap dou G by dou Z. That equals 2x plus 4 into I cap plus j cap times 2y minus 6 plus k cap times 2z minus 8. This is the gradient of Z. Now we have to find out del F at the given point P equals 4 comma minus 3 comma 2 because we want a normal to the first surface F at the given point P. So we have to find out del F at P. Del F at P equals 8 I cap minus 6 j cap plus 4 k cap because in del F we have to substitute x equals 4, y equals minus 3 and z equals 2. Now we need to find out del G at the point P, which is the normal to the surface G at the given point P. To find out del G at P, we need to substitute x equals 4, y equals minus 3 and z equals 2 in del G. So del G at P equals 12 I cap minus 12 j cap minus 4 k cap. To find the angle between the given spheres at the given point, now we need to find out the norms of the del F and del G. Norm del F at P is equal to square root over 116. Norm del G at P equals square root over 304. You can find them very easily. Now, we need to find out the dot product of these two vectors del F at P and del G at P. Their dot product equals 152. Now the angle between the given two spheres at the given point P is nothing but the angle between the normals del F at P and del G at P. So the angle is given by cos theta equals del F at P dot del G at P divided with norm del F at P norm del G at P, which is equal to 152 upon root over 116 times root over 304. So far we have learned the definition of partial derivative, the definition of the gradient with a few examples, and properties of the gradient of a scalar field. Next we solved a few problems. If we want to find out a normal to the given surface, we need to find out the gradient of the given surface. If we want to find out a normal to the given surface at a given point, what we have to do? We need to find out the gradient of the given surface at the given point. That gives us the normal to the given surface at the given point. If the angle between normals is asked, so what we have to do? Then we need to find out the gradient of the function at the given points. Next we have to find out the unit normals n1 cap and n2 cap. The angle between them is given by the formula cos theta equals n1 cap dot n2 cap by norm n1 cap times norm n2 cap. If we want to find out the angle between two surfaces, we have to find out the angle between normals to the surfaces. We have to observe a few things now. What happens if we take the dot product between del f and I cap? Suppose W is equal to f of x comma y comma z is a given surface. If you find out del f dot I cap, then del f dot I cap equals I cap dou f by dou x plus j cap dou f by dou y plus k cap dou f by dou z dotted with I cap, which gives us dou f by dou x. Similarly, del f dot j cap gives us dou f by dou y, del f dot k cap gives us dou f by dou z. What are these three? Dou f by dou x is nothing but the derivative of the given surface in the direction of the x-axis. That is given by del f dot I cap. We can say it's a directional derivative of the given surface f of x comma y comma z in the direction of x-axis, namely in the direction of I cap. If we want the directional derivative of the given surface f of x comma y comma z in the j cap direction or in the y direction, we need to take del f dot j cap, which gives us dou f by dou y. So what is dou f by dou y? Dou f by dou y is nothing but the directional derivative of f in the direction of y. What is dou f by dou z? Dou f by dou z is the directional derivative of the given surface W is equal to f of x comma y comma z in the direction of z. It is given by del f dot k cap. So here the partial derivatives dou f by dou x, dou f by dou y, dou f by dou z, they give us the directional derivatives of the given surface in the direction of x-axis, y-axis and z-axis respectively. If we want the directional derivative of the given function in the direction of the x-axis, we took the dot product between del f and I cap. Similarly, if I want the directional derivative in the direction of y, I took the dot product between del f and j cap. If I want the directional derivative in the direction of z-axis, I took del f dot k cap. But I don't want the directional derivative in the direction of x or in the direction of y or in the direction of z. I want the directional derivative in the direction of some vector, say u cap. How to find the directional derivative of the given surface in the direction of some prescribed vector u cap? To answer this question, we have to learn directional derivatives, which are also the applications of the gradient. That we do in the next lecture. Throughout this lecture, our main focus is on the gradient of a scalar point function or a scalar field. For further queries, please contact me through email. Thank you very much.